Welcome everyone. Thanks for joining. We already have our presenter, Stephen Moore, with us, and it's going to be a wonderful presentation, I think, right in the time when we need it. So the topic, as you all know, is understanding irrigation components to improve water use efficiency for residential and commercial landscape. Stephen Murray, he is a landscape architecture graduated from Utah State University. And he gains hands-on experience in landscape and irrigation system design, working as a landscape contractor at a wholesale irrigation supply company. In 2021, he founded Irrisoft, where he developed and patented Weather Reach, smart irrigation control technology. His company, Murray Water Management and Irrigation Consulting Business, helps organize and use water wisely. He is very much active in this landscape and water world, and he has, I think, 30 years of experience, right, Steve? I think that's more than that. So now with that, it's all to you, Steve.
Oh, thank you. It's exciting to be here. I appreciate very much the opportunity. We're going to be talking about landscape irrigation, and my passion is efficient water use and beautiful landscapes. And yes, that's what I've been doing all my career. And I've learned a few things, and I hope I can share some things that'll be of value to you. I have learned one thing that comes up pretty often is that people don't waste water, but their neighbors do. And so I'm hoping that people will take a closer look at their own water use. And there's also a fear of conservation because, oh gosh, if I cut back on my water use, it's going to hurt my plants. I can't tell you how many times people have said, Steve, thanks so much for helping us reduce our water use and save money. And the landscape's been actually healthier because it's getting the right amount of water when it needs it. Now, I've been asked to talk about irrigation components and how we utilize those components to improve water use efficiency. When we think about components, each component is within a system, and that system is and those components are there to solve problems. I think it's really important that we begin understanding the problem that we're trying to solve. And so that's where I want to begin the discussion today, is looking at the problem. And as I think about water managers, they sit on a stool watching to see what's going on, which is a good thing, but that stool has 4 legs. And they depend on those 4 legs has specific purpose. And if one of those legs breaks or isn't done right, they're going to topple off that stool. Well, what are those 4 legs? Soil is a key part of sustaining a plant, but we've got to get water to that soil. And so we're going to use an irrigation system to deliver the water to the soil. And but just having an irrigation system by itself isn't going to get the water to it. We've got to have a control system. And fortunately, control systems now are smart, where they can react to weather conditions. But just because they're smart doesn't mean they've been taught enough. So the 4th leg is telling that control system information about the landscape and about the irrigation system so that it can then create an irrigation schedule. You kick out any one of those legs, you don't respect the soil, you don't have a good delivery system, you don't have a smart control system, or you haven't programmed things correctly, you're not going to be an effective water manager and use water efficiently. So that's the point I really want to drive home, is that we have to consider all 4 elements. Well, let's start with the basics. Plants need water, they need air and nutrients and so forth. But the plants don't get water from our sprinklers. They get water from the soil. And the purpose of the soil is to deliver that water to the plants, because that's where the plants are going to get that moisture. Our job as irrigators is to refill that soil reservoir. Too many times people think, oh, yeah, the dirt's, I got the hose out and I watered, but if you water for just a couple of minutes, you get the top wet, but you've got to think deeper, because those roots are down deep. And when you have a deep, healthy root system, that plant is going to thrive. And that's the whole point of having a landscape is make it beautiful and make sure that it gets the things, the resources that it needs to thrive. Here's an odd place to start, but I think it's an important place to start. We're taught about hydrozoning as landscape designers, where we're grouping plants that have similar water needs together. Well, once they've been grouped, now it's time to irrigate those. And how do we irrigate those? We have to consider what that group looks like, the plant type, the exposure, the application rate of the sprinklers. Each zone, hydrozone, will have different watering requirements. So let's make sure we understand how those watering requirements would affect our decisions relative to hydrozones. The soil is a reservoir, and that's where the plants are going to get their water from. But that soil reservoir, as all reservoirs do, they have a capacity. And the capacity of that reservoir is based on the soil type and the rooting depth. I like to use the example of a glass with ice in it and a straw. The ice represents the soil particles. Well, if you fill that glass up, how much water can you get out of the glass? Well, it really depends on how far you put the straw in. If the straw only goes down an inch, you're not going to get a whole lot of water out of that glass. We've been taught the importance of deep, less frequent watering. So we need to make sure that we are managing our irrigation in such a way that the roots can go down deep, so we can implement that deep, less frequent watering principle. Another point that I think is essential to understand is the balance between air and water in the soil. The organics and minerals make up a portion of the soil, but then you've got the pore space, and that's never going to be exactly 25% air and 25% water. It's going to be changing. It's dynamic. The more water we put on the ground, the less air that's in the soil, and vice versa. And as you water deep and less frequent, what happens? Water dries out the air, but as the soil begins to dry out, air is drawn back into the soil. It's almost like a very natural respiration process where watering is an exhale, and then as it dries out, the air is drawn into the soil. And so that's an important thing to remember, is the importance of a balance, a healthy balance between water and air in that soil. Now, as an irrigation manager, you need to really understand soil moisture content. I think we can all visualize bone dry, no water at all in the ground. Plants are not going to survive, period. We go to the other extreme and look at a saturated condition. And in a saturated condition, all the pore spaces are completely filled with water. There's no air, and that's not healthy at all for the plants. In a saturated condition, the water begins to drain as the result of the influence of gravity. When drainage stops, the soil moisture content is considered to be at field capacity. And field capacity is, think of it like a sponge. You put a sponge in a bucket of water and squeeze out all of the air, pull it out, and the water begins to drip off that sponge. When it stops dripping, that sponge, or the soil, if you will, is at field capacity. But if you squeeze the sponge, you got lots of water in that sponge. So at field capacity, there's still plenty of water in the soil. To make sure we have a good balance of air and water, we allow the soil moisture to deplete, not to a wilt point, but about halfway. The industry refers to this as being MAD, managed allowed depletion. And as a general rule, 50% allowed depletion is a good target, but that's a fuzzy line. That's not an absolute, because you still have water at 60%. You still have water at 70% depletion, but it's just a little tougher for the plant to get at, and you're going to begin to reach a stress point. So we irrigate to allow depletion and then restore it back to field capacity. With that in mind, what causes depletion? Now, you're going to see how all of this begins to tie together here in just a minute relative to hydrozones. Depletion is a result of evaporation and transpiration. The industry refers to the big word ET, or evapotranspiration, It's the loss of water from the soil through evaporation and the loss of water through transpiration. Transpiration is the water that evaporates through a leaf. There are principally four climate elements that drive evaporation or ET. Solar energy is the biggest energy source that causes evaporation, changing that liquid into a vapor. And then temperature is a second. Wind accelerates evaporation because if you think about it as if you've turned it into a vapor and then you blow it away, you now are replacing that with drier air, just like a hairdryer. So wind accelerates evaporation. Humidity, on the other hand, will influence the rate of evaporation. In a very dry climate, it's very easy for water to evaporate. It doesn't take as much energy as it does when that soil is already loaded with a lot of water vapor. So that's why it's easy to dry clothes out or dry things out in Arizona as opposed to New England, where it's much more humid. So all of those are the factors that drive evaporation and transpiration, or ET. There's a difference, though, between actual evaporation and what I'm going to refer to as the industry refers to as the potential for evaporation. The potential for evaporation says I look at all of those conditions and I can estimate how much water evaporated if that water is there. To actually measure the real evapotranspiration is very costly and is specific to every single location within a landscape. So we need to depend on an estimate. We can go to the Utah State Division of Water Resources website at conservewater.utah.gov and look at the information that's there. They have weather stations throughout the state that are taking these measurements and calculating an ET value and presenting it either as today or in the last 7 days or even yesterday. You can see that there's some differences, and that's expected. And then you can also see that there is a lawn watering guide that's going to influence or tell you how often you should be watering by county. And that's some good, helpful information. But all of that is driven based on ET and the potential for evaporation. But transpiration is not always exactly what we expect it to be because plants resist evaporation and different plant types resist the evaporation differently. A cactus, let's go to the extreme. A cactus is going to hold on to that water as much as it possibly can. And so are many of our desert plants in Utah. They resist evaporation. Whereas a turf grass is going to freely evaporate. As soon as we throw mulch over the soil, we have protected the ground against the evaporative source energies. Shade influences or decreases those evaporative influences. If we can put the roots down deep, that water that's down deep is not subject to the same evaporative forces. So we need, now that we understand ET and the fact that the environment or the plants are going to affect the rate of evaporation, then we can begin to apply what is referred to as ET coefficients. Some people call it crop coefficients or plant factors. Here's where it all ties together. We don't put low water use plants in the same hydrozone as a cool season turf because their ET coefficients are different. And that way we can manage the frequency of watering because we understand that those plants are going to use water differently. And also the rooting depth is another factor that comes into play relative to hydrozoning, and we've already talked about that. Exposure is another factor that should be considered in hydrozoning because in those full sun conditions, it's going to dry out much faster than it will in shade or partial shade environments. So we keep our hydrozone respecting the plant differences, the rooting depth differences, and the exposure differences. There's one other factor that we mentioned as we talked about hydrozone, and that's the fact that sprinklers apply water at different rates. Spray heads put down water extremely fast compared to drip systems. And rotors are a nice mid-range application rate. But those are also not exact. Spray heads, their application rate varies. Rotary streams and rotors vary. Drip systems can vary dramatically. So we make sure that the application rate within a hydrozone is going to be kept the same. By having that uniformity within a zone, we can more accurately manage the irrigation schedule. So let's review. Hydrozones, plant type, rooting depth, that's a factor. Exposure is a factor. And then the irrigation application rate is a factor. So we're going to irrigate each hydrozone as needed based on the conditions that exist within those hydrozones. Before we dive into sprinklers themselves, let's make sure we understand uniformity. The objective of a sprinkler system is to deliver water to the soil, to refill that soil reservoir. And the more evenly we can distribute that water, the better. I'd like to also point out that we do have capillary action, capillary movement that can move water. And when you water deep and less frequently, you do get more lateral movement than when you water very shallow and more frequently. So that's another reason why it's important to water deep and less frequently. But when we think about uniformity, the first thing we have to consider is what are the how is water being delivered by those sprinklers? And they're round patterns. All sprinklers throw a round pattern, but we put them into square spaces. So we have to look at where we position those and how we position those in terms of our layout and our spacing to get as uniform as we possibly can. The other thing we have to do is watch what is referred to as matched precipitation rate. If we think about this full circle sprinkler, it's watering 4 times the area that this little quarter circle sprinkler is watering. So this head should put out 4 times as much water as the quarter, and the half is obviously going to put out half as much as the full head. So making sure that we match the gallonage for those zones is an important process. Uniformity is also driven a lot by pressure. We get into high pressure situations and the performance of the nozzles falls apart. We get a lot of loss to evaporation. We get more water we get lost through drift. And the uniformity is not as good as it is when the pressure is optimum for that nozzle. Nozzle performance does differ from manufacturers. I've seen some nozzles that are fabulous and other nozzles that are just pathetic. So your designer will know who's got good nozzle performance to make sure that you've got good distribution. And of course, a water audit's going to give you the best indication of how your uniformity is, and the water check program can help with that effort. Now, here's an interesting statement. Dry spots waste water. Why do I say that? Probably the most common question I would get or concern that people would raise is, hey, I got a dry spot. Well, what's the first reaction when you have a dry spot? You turn up the timer on the sprinklers. And so it waters more. But wait a minute. You just had one small spot and you just turned up the sprinklers, and so the entire zone is going to get more water. The problem is it should not be solved by turning up the time. The problem should be solved by looking at the head layout, the spacing, the pressure, the nozzling, and the head adjustment and making sure that you're delivering water as uniform as possible so that you do not waste water. So watch for dry spots. That's the big battle. So let's talk about, fingers right. There we go. Irrigation system components. We're going to walk through all of them, the basics, and just cover some key points that I think it's important for people to remember. Spray heads, everybody knows what spray heads are. They're going to be great for turf and shrub areas and smaller areas. Many different nozzle patterns from anywhere from full circle to variable arc, and a distance of throw from 5 to 15 feet. Lots of pop-up heights. Now, there's a lot of architects that really push hard for a 6-inch pop-up even in turf, because you want that nozzle to be high enough above the grass blades so that it does not interfere with the spray pattern. So that if you're going to be on that higher mowing pattern, which is recommended, you may want to consider going into a 6-inch pop-up. Head-to-head spacing is going to be important. Match precipitation is just inherent in the nozzle design. You've got a very broad range of flow rates, and so that has to be understood as you're creating your hydrozones. The application rate with spray heads is high. 1.5 to 2 inches per hour. That's oftentimes faster than what the soil can absorb. And so it's probably best to look at something else or go into a cycle and soak. Because of that the cycle and soak is a good mitigating approach, but there are other lower precipitation rate options that I'm more in favor of in mid-size areas. The other thing with spray heads that's important to remember is pressure. It's most of the time we see those nozzles misting. They should not be misting. If they're misting, you've got too high of a pressure. And there are heads now that have a pressure regulator actually built right into the stem. And I'm a huge fan of those pressure regulating spray heads. They do a great job. The multi-stream rotor was introduced a couple decades ago, and just a fabulous invention. They really do a very nice job. They are for those small to medium areas, throwing anywhere from about 12 to 20 feet. And they have a low precipitation rate. That's the thing I really like about them. Plus, their uniformity is much better than spray heads. So look for those multi-stream nozzles or rotors. They fit on spray heads, so that's really nice. But they do have longer run times because there's a lower application rate, and so that's a good thing. You still have to do your head-to-head spacing, and your pop-up height is still going to be respecting the same issue of making sure the stream is not being blocked by any of the sprinklers. Rotors, on the other hand, are not multiple stream, but a single stream and carrying bigger distances. You know, you can get easily 80 feet out of a rotor, anywhere from 20 to 80 feet out of a rotor. For large and medium-sized areas with a huge range of nozzles. And you're going to have to be careful on nozzling with rotors, because that's where you can get in trouble of not having matched precipitation rate. You've checked that gallonage and check, is this a quarter head, a half head, or a full head, and what's the appropriate gallonage on that head. Rotors do have a lower application rate, which is good. Usually they don't have multiple pop-up heights, but they're usually high enough to get above the turf. And sometimes pressure regulation is going to be very important with rotors. Drip irrigation, yes, I'm a fan of drip irrigation, but it's a matter of making sure you're putting that water where it needs to be. Flow rates can be anywhere from 1/2 to 5 gallons per hour out of a single emitter. Your application rate is very low. Drip is going to require pressure regulation, and you're going to need a filter. But the nice thing is you're putting that water right at the base of the plant to get it to the roots. You're not spraying it up in the air, so it's a much more efficient means of delivering water. Microsprays, there's some pros and cons to microsprays. Yes, it's a spray, so you've lost the benefit of having it deposited right at the base of the roots, or right at the base of the plant. But if you've got a bed had lots of plants in it, then maybe it's a good thing to just go ahead and spray it. But these are on a fixed riser and they sit above the plants. They are very adjustable. They are small, but they are nevertheless subject to vandalism or damage. But microsprays may be a solution that some people haven't tried that I think they do a nice job. I know I use them in my garden in a couple places. I am a huge fan of these little micro bubblers, and they don't get used as much as I think they should be. They're nice little streams of water. You turn that and you can adjust the flow rate. They do require pressure regulation and filtration. But as you can see, they're watering very low to the ground and spraying out a stream of water and delivering water to a number of different plants at the same time. So micro bubblers are a sweet little solution. Drip line has become very popular in the last couple decades, and there's some pros and cons to drip line. It's easy, but it's also a pain. The The nice thing about it is that from a design standpoint is you just, say, hey, yep, there's the zone that I need to water, and I put in my drip line and we're done. But, and you have some advantage of the water just being deposited right on the ground, or if you can put a mulch over that, which is even better. And that's going to hide the drip line. This is a bed that has not been finished yet, and there's no mulch on it yet. But the one thing you have to be careful of is it's really easy to start watering places that don't need water. And so that's the downside to a drip line. There are applications where drip line is used below surface, where it's buried under the turf, and it's also being used in agriculture for the same use, where it's depositing that into the root zone, and so it's not subject to the surface evaporative influences. So drip line is an excellent solution. I've seen people get a little carried away and get some fairly high precipitation rates on drip line. So do watch that precip rate. That's going to be based on your emitter spacing and your line spacing, as well as the emitter output, because they can range anywhere from 1/3 of a gallon per hour to almost a gallon an hour. Drip line is going to require pressure regulation and filtration, but drip line is a good solution. If we look at the drip components as together within a system, you're going to bring pressure to the valve, put in a filter, a pressure regulator, and then that's going to go to your distribution piping. And generally that's going to be 1/2-inch poly. Sometimes it may be 3/4-inch poly going down to a 1/2-inch with various sublaterals. Then coming off of that lateral tubing is going to be a 1/4-inch tubing that goes right to the water outlet, whether that's a stream bubbler or an emitter or a micro spray, or going to your drip line systems. So those are the main components that you're going to see within a drip zone. Filtration is obviously going to be needed in dirty water applications, and you need to look at, there's basically 2 flavors. You're going to have a screen type, or what is referred to as a disc. Screen is just going to have perforations, holes that would filter out the contaminants. The discs think of it as almost like a 3-dimensional filter. You have little grooves, and the water passes through those grooves. So disc filters do a very nice job with organics in the water, and are good really for drip applications. When you're looking at filters, you're wanting to look at what is the flow rate that has to be supported by that filter, and how much contaminants you're expecting. It may be that you'll have to oversize that filter because you're expecting a fairly high contaminant load. Then how clean do you need that water? That's really based on what the sprinklers are. Spray heads, there's a debate between 32 mesh or 50 mesh. Drip is traditionally going to be 140 mesh. And so that the higher the number, the smaller the holes within that filter. Pipe is just going to have to do its job. We got 2 different types of piping systems generally within an irrigation system. Your main line, or your pressure pipe, is going to be delivering water from your point of connection all out to the individual zone valves. And then from the zone valves, you're going to go through lateral piping. Generally, in the irrigation world, we're working with either PVC or polyethylene piping. Most of the time, I recommend Schedule 40 PVC up to 4-inch. You can see here with this 1-inch pipe how much thicker that wall is on Schedule 40 than it is with a Class 200 pipe. This is, they're both going to hold the pressure, but that Class pipe in smaller diameters is just more subject to damage because it doesn't have the same mechanical strength that the Schedule 40 does. Your polyethylene pipe, high density, is a black flexible pipe. It's the nice thing about it is you can snake it through. You don't have to have as straight of trenches. You don't have to worry about draining it in the wintertime, although some people do. But it's poly is becoming very popular for both main lines as well as for lateral lines. Although sometimes you'll see just PVC main lines and lateral line being polished. The key thing to remember with piping is getting your pipe sizing correct. It's essential to recognize or to count up the flow rate on each zone and make sure you don't exceed the hydraulic capacities of that pipe. If you start pushing too much water through a pipe, you get too much pressure loss. And so you end up with a big difference in pressure between the first head and the last head on a zone. So pipe sizing is all about supporting that the pressure that those heads need to be uniform. Every system's going to have some valves, and there's lots of different types of valves that can be used in a system. Let's just start at the point of connection. You'll use a stop and waste valve traditionally, where that's buried deep down at the same level as the water meter, or the water line coming into the building. And it's called a stop and waste because it's going to stop the water and it's going to waste that little hole right here, wastes the water or drains the water on the downstream side of that valve when it's closed. So when you shut off the system in the fall, the water drains through that hole, and that's the first step in winterization. And there may be other points on the main line or laterals that need to be drained as well, but that's the first point of connection valve that you're gonna have to deal with. Codes require that we have a backflow preventer, and there's really three flavors that we consider: reduced pressure type or RPAs, pressure vacuum breakers or PVBs, or double checks or DCAs. Now, the pressure vacuum breaker, the PVB the RP is the highest level of protection that you can get. These do need to be installed above ground, and but this is the best you can get in backflow, so you can protect any contamination from the sprinkler system getting back to the culinary or potable water system. Pressure vacuum breakers are good as well, but they have to be installed above the highest sprinkler. RPs, you don't have to worry about that. A good acceptable solution is double checks. They can be put into a valve box and do a good job. All of these, notice, have little test ports, and those should be tested on an annual basis. So the other thing to remember is the importance of managing pressure. Pressure is tied to uniformity and better performance of those sprinklers. So a pressure regulator may be installed at various points in the system. Isolation valves are really there for convenience of management of the system. If you've got to take down an area for some maintenance or repairs, then you can begin to isolate a portion of the system rather than shutting down the entire system. Drains are in freezing climates are going to be essential. Although some people do just use compressed air to blow out the systems. But you may need to put in some either manual drains or automatic drains. I would never use automatic drains on the main line. That's just I just have a real aversion to that. But on laterals, I'm not opposed to that at all. There's a valve that doesn't get used as often as I think it could be because they're really handy, and that's a quick coupler valve. These are tied to the main line, and that cap is sitting right above grade. You lift that cap and put in the key, and you have a source of water to do any manual watering. So putting those at convenient locations around a property makes a lot of sense. Now let's take a look at the automatic valves and consider some of the things there that are essential to remember. Automatic valves, the brass valves that's traditional, but most people are using plastic, and plastic valves are great. You've got to think about the actuation, whether that's going to be a 24-volt AC circuit on the solenoid or a DC latching. The size of that valve is going to be based on the flow rate. If you put in a valve on a line that's going to be flowing higher than, lower than what the valve will support, lower than the valve will support, it may not shut down. Most valves have a flow control that limit how far that diaphragm can open. And this valve we see has got both a side inlet as well as a bottom inlet. The water spills over this edge. That edge is being blocked by the diaphragm. And the pressure on the top of the diaphragm is allowed to remain high while the solenoid is closed, so that keeps the valve closed. As soon as we lift the plunger in the solenoid, when it's actuated, the pressure is relieved here and that diaphragm can lift and the water will spill over that valve seat. It's a common accessory is to put in a pressure regulator that can then modulate that diaphragm and control the pressure coming out of that valve. And again, I highly recommend pressure management. Manifolds are just there to make it easier for you to service those valves. Having manifold systems are great. I really am a big fan. They've got unions on either side of the valve to be able to service those valves. And let's keep going. Wiring and control stuff. Typically, you're going to be using either 14 gauge single strand wire or multi-strand 18 gauge wire. 24 volt AC valves need two wires, a hot and a common. Hot is unique to every single valve, and the common is going to be common to all valves. And generally with multi-strand, it'll be white. When you're using single strand, it's generally you'll see the white wire issue or valve. Decoders are becoming very popular. They just have a two-wire path that follows the main line to every single valve, and then you put in a decoder in the valve box, and the decoder may support one or up to four valves. And they're addressable, and so they have to be programmed. But it's a very simple way to add a valve or to be ready to support expansion on a site. Two wires becoming a very popular solution, particularly in commercial applications. Don't forget to use watertight wire connectors, please. That's just a must. We're seeing a trend on more and more radio-controlled or wireless valves, where there's a transmitter at the controller that reaches out to the valve box and actuates that valve. So that's a handy solution. I'm looking at the time. Am I in trouble here, Sethal? Oh goodness.
No, we have 20 more
Oh,
minutes.
hey, I'm looking at the wrong timer. There we go. We're in good shape. I was looking at the timer on the on one screen and not the timer on my clock. We're good.
Okay.
We're good. Good. Okay, control systems. Here's my passion. I love control. I love smart control. I, of course, was involved with that for many years. In the early days, we just used dumb timers, and they automatically wasted water because they were just not programmed very often. They were set and forgotten. Fortunately, we are pretty much away from dumb timers. Nobody should be buying a dumb timer anymore. You should be buying a smart controller. Smart controllers are weather responsive, or they respond to soil moisture sensors. The EPA is now backing smart controllers by saying, here is a test protocol. If that manufacturer's product meets that test protocol, it gets the EPA WaterSense mark, which indicates that it is complying with that test protocol and is an efficient water management device. Most smart controllers too are tied to a smartphone app, which makes it really easy to turn things on and off or make changes to your schedule from your phone or wherever you may be. But the key thing is smart controllers are saving water and are doing a good job. Now, I highly recommend getting a designer to help you with an irrigation system. And if we look at the components within that irrigation design, we're seeing a point of connection. And then we got this little symbol here. What's that little symbol? Well, there we go. We go to the legend, and it's a little stainless ball valve. So that's an isolation valve. Then we got the backflow preventer. Then we've got the screen's hiding things, and so I'm not exactly sure what's right there. Can I move this? Yes, I can move that. There we go. Master valve. There's our flow sensor. What's that symbol right there? We can go and take a look at our legend, and we can see that it is it's a quick coupling valve. So that's great. We've got a quick coupler right here. Then we've got our main line that's going out to our zone control valves. And notice now when we start looking at our zones, we have this zone right here, which is drip line. We can see each of the lines within that drip line system, and that's tied to one zone. We have a separate zone because this has a different water requirement than this area out here, which is most likely turf. Notice that they've also put the full heads on one zone and the part circle heads on a separate circuit. That's a good management approach. That way we can water our full heads twice as long as our part circle heads, because they need to put down more water because they are watering a bigger area. And so that's a very common practice, to see those full circles on a separate circuit. And a good plan is obviously going to have its legend, and you can follow through that legend and learn what each one of those symbols is representing. So now if we go back to what we talked about in hydrozones, we talked earlier about the importance of hydrozone respecting or being divided based on plant type and exposure and sprinkler application rates. And so how does that all tie in? Well, we have to control the frequency of water. We say deep and less frequent. Well, we have to control that frequency. And of course, that's based on managed allowed depletion. We'll talk about that here in more detail. But plant type is going to drive your rooting depth and your crop coefficient. It's going to be affecting your exposure, is driving your frequency. So those are all related. Your zone runtime is related to that sprinkler application rate. So it begins to carry forward into more detail than just how we hydrozone. It goes into the control side of watering that zone. Now, when we look at a smart controller, it's looking for some settings, and it's asking the question, okay, what is that soil type? What is that root depth? And from there, it can determine how deep or how much water should be applied. And then how long should those water runs? Well, that's going to be depending on how many inches we've got to apply and what the application rate is. And of course, uniformity has to be considered. So how much do we water? Root depth, soil type, how long, how quickly it applies, and what that uniformity and how much we're trying to apply. How often? Well, we're going to go smart. We're going to be based on managed allowed depletion. If we look at this chart here, here's a quick and dirty, but it's not meant to be exact. Don't follow it. Just use it. It's kind of a guide. Spray heads, your precip rate can be a range of 1.3 inches an hour to 2 inches an hour. So that means to put down a half an inch of water, you'd be watering from 15 to 23 minutes. The state really pushes for that half inch of water at least. And here's another example. If we look at MAD, we can say ET was 0.15 in one day, then a tenth of an inch, another 1500ths of an inch, another tenth. We've now hit our allowed depletion. And so now it's after 4 days, it is time to water again. And again, the half inch is a good target, but it again is based on your soil type and the rooting depth on your plants. I know for myself at my home, my roots are down much deeper, and I'm watering about every 10 days on my turf here in Logan, Utah. So it really ties down to what is that root depth and the soil type. The industry has an expression, an old expression called the ET checkbook. The newer term is a moisture balance system, and smart controllers use this approach. And how does it work? Why do they call it the checkbook? Well, a checkbook's got withdrawal and deposits and balances. What's a withdrawal from a checkbook, an ET checkbook? Well, it's ET, because that's evaporation. It's a withdrawal. It's drawing things out of it, drawing water out of that soil moisture. A deposit's going to come from rain, and it's going to come from irrigation. So in this case, on the first day, we had a little bit of a withdrawal of ET, and we had a little deposit coming from some rain. And so we didn't need to irrigate. And we get a little more ET, and it's finally time to irrigate. So here we get some rain. And so in this case, the system is tracking that balance and deciding when and how much to irrigate based on this ET checkbook or a soil moisture balance method. To do it really right, you need not only an ET measurement, but you also get a rainfall measurement. This is one of the weaknesses of some of the smart controllers, is they don't always measure rainfall as accurately as they could be, because rain can be so variable in a given city. One other point that I think it's important to remember in setting up the control system is you want to reduce your runoff by cycling and soaking when the sprinklers are applying water faster than what the soil can absorb. You apply water just to the point where it's about to run off, and then you stop and you let it soak into the ground and you hit it again. And that's the cycle and soak. And I've seen that solve so many problems, and I'm a huge fan of cycle and soak. Improving water use efficiency. This is going to be more of a review than anything, but you know, the phone calls I would get, we've got dry spots. How do we solve those dry spots? Well, we're going to look at the heads. Always look at the heads when we're talking about dry spots, or well, I shouldn't say always, and maybe you're dealing with the soil condition. But the pressure may be too high or too low. You may have the wrong nozzle. There may be some head adjustments that has to go along, or it may be just simply a crooked sprinkler. Now, there's a big difference between a dry spot, a small area within a zone, or a dry zone. If the overall zone is not looking good, then you're probably dealing with a valve runtime issue. Most likely that's the problem. It could be a watering frequency issue, but most of the time you would just need to increase that valve runtime. Now, if the entire site is running dry, then watering frequency is going to be the issue. You're waiting too long to start watering. Now we can flip these two around and look at the inverse. If I've got a wet zone, adjust my runtime or my frequency. If I've got a wet site, adjust your watering frequency. Now, smart controllers use the weather to adjust those schedules. You start with an initial setting, but things can change. Roots can grow deeper. And so if you can be changing those root depth settings and those ET coefficient settings over time, you can get to the point where I'm at, where I watered last year on my lawn in Logan, Utah, 11 days. The entire season, I watered 11 days because I have deep, less frequent watering. It took me several years to get to that point. But that's okay. I've got the years to do it. Let's go, it's a gradual change because you can teach those roots to go deeper in the spring and the fall by adjusting that root depth setting and decreasing that ET coefficient. And you can get some excellent results with a smart controller that will help you make that landscape thrive as well as using water efficiently. Those are the points I wanted to make. And I'm ready for some questions, Chital. And hey, I think I did pretty good. Look at that time.
Yeah, you're right. Right on time, and we had pretty good discussion in the chat section while you were teaching this. Thank you, everyone. Now we will move to our question sections. Let's move on to the questions. Nancy Smith asks, you may answer going forward, but what does one do in an existing irrigated landscape that has spray heads for bedding plant and large pots within the same zone on drip? Obviously not ideal. I'm currently doing a longer drip main program of watering and then second program with shorter irrigation time, more frequent days. Is this all I can do? You want to take that? It's in the Q&A if you want to read it again.
Yeah, let me read that again if you don't mind. You say it's in the Q&As, right?
Yeah.
Here. Yeah, if she really wants to take it seriously, those wireless valves are a nice solution. That's an easy way to get that done because she's in a situation. This is why I was emphasizing hydrozones right out of the gate. She has essentially two hydrozones. She's got her bedding plants and she's got pots. And so the pots obviously are going to have a different watering requirement than plants that are in the ground. So if she's got a lot of them, would make sense to put those on a separate valve. I don't know the details, but
yeah.
That would be one alternative. The other thing is, the concern is how well drained is that soil. If it's a well drained soil, it's going to be a little more tolerant of more frequent watering. But you always have to water to the worst case, right? Yes. And otherwise, if you're watering to the most the least water use plant, then the rest of the zone is going, the other part of the area is going to suffer. So
Yeah. And one thing, Steve, I would like to add here is what I do. Like I have trees in my turf area, and I need to water them deep. I don't have a designated drip lines for the trees. So I take my hose, make it really low, and let it soak for 8 to 9 hours so that the water go really drip deep. And that way, I'm making sure my large plants are growing the roots deeper. That might be a manual remedy. Something automated would be changing the valves, I think.
right. No, I do the same thing. We deep water our trees about once a month up here.
Yes. So Annie Christie asked, where can I get the disc filter, brand name or to search online?
Amiod and Netafim make disc filters. They and a good irrigation supply house wholesale is going to should have that. You're probably not going to find it at a Home Depot's or a Lowe's or some kind of or a garden center. You're going to need to go to a professional irrigation supply house.
Awesome. I think we are well above our time. That was a wonderful presentation. And with that, thanks. Thank you.
Thank you.